Hello and namaste. My name is Brandon, and welcome to the next video in my series on basic time series. In this video, we will learn about our next forecasting technique called linear trend projection, and we will take a very visual approach. So as always, if you find this video helpful, please like, comment, share, and subscribe. Let's get started. So here's the data we've been using in this series. It is Nigeria's GDP per capita from the year 2000 all the way up to the year 2020. If we graph it, it looks like this. We can see a very sharp increase from the year 2000 all the way up to the year 2014, 2015. It almost doubles during that time, and then sort of flattens off from 2015 out through 2020. So using this data, let's create a linear trend projection forecast that may look something like this. First, a little background so we know what it is we are actually doing in linear trend projection. So whereas the simple moving average, the weighting moving average, and the exponential moving average use a series of weights on past values, linear trend projection can be seen as our first modeling technique. Linear trend projection looks at the trend of the entire time series all at once and projects forward in time under the assumption the pattern will continue. If you've ever worked with linear regression, linear trend projection will be very familiar. The technique finds the slope and intercept of the entire time series and creates a linear model. While this video will be about a straight line model, curvilinear models can also be used, but be very careful about overfitting. As soon as we start bending our model to the data, we risk serious overfitting issues. What linear trend projection answers is this. For each one period change forward in time, the level of the measured value on the y-axis changes by some amount. In our Nigeria GDP data, what linear trend projection will find is the change in GDP per capita for each 1 year step forward. Linear trend projection will indicate the level, the y value on the y-axis, and direction, which is the sign of the slope. Is the trend increasing, decreasing, or relatively flat? The forecast error is the distance between the actual data and, in this case, the straight line model. So we ask the question, how consistent do I think the time series level, including any directional change, will be over time? If you answer that consistency question by quite a lot, then linear trend projection is a good choice. If you think that trend consistency is only moderately strong, then maybe a curvilinear model might be a better choice. So a polynomial model, exponential model, etc. Again, a high risk of overfitting by artificially bending the model. So when we project forward in time using linear trend projection, we are assuming that that trend will continue into the future, obviously. But if we start bending the model to the data, then that future projection might be a lot worse. Excel can make linear trend projection very easy with its functions and graphing capabilities. It can easily add trend lines, equations, and so on. And I'm sure Google Sheets can do the same thing. So Excel will be our friend here to make this a lot easier. Now there are some downsides and caveats to linear trend projection. Linear models have the characteristic of being very generalizable. They are unlikely to overfit the data. The flip side is that linear models do not fit bendy data very well, which can lead to large errors. They can be deceptive, and that one area of the time series that is under forecasted can be offset by another area that is over forecasted. But this is the best fit line in action. That's what it does. A valuable quality looking forward is that linear trend projection opens a world of more complex modeling opportunities where we integrate other explanatory variables. Now let's actually do the projection using Excel's tools. We graph it again, add a trend line, and we're done, basically. So when we add the trend line in Excel, we come up with an equation of y equals 56.371x plus 1601.4. We have an r squared of 0.8, but usually in time series like this, we don't use that very much, but I put it on the graph so you can see how well the line fits the data. We just add the trend line in Excel and you have the slope and intercept. Very easy. You could also use the actual slope and intercept functions in Excel with GDP value as y and time period vector as x. So here is our equation. So y equals 56.37 times x plus 1601. I went ahead and rounded just to make it a bit easier to work with. Our first term is the slope, and it says that over this time period, each year on average, Nigeria's GDP per capita increased by $56.37. So we can see the magnitude of it in dollars and the sign of it. Since it's positive, we know that it's increasing. Now the intercept over here is just the algebraic location on the y-axis where the model intersects, so times 0. It's usually not that important as we focus on the trend and the magnitude of the trend that we find in the slope. But it is an equation that we can use to graph the line. Now the way this works is that we substitute the time period into the equation. So here's the equation again. We can see in the fourth column, all we are doing is substituting the time period, so 1, 2, 3, 4, and so on, into the place of x, and then going ahead and evaluating that equation. And that generates our forecasts over in the last column. So the forecast for 2021, that's our last unknown value here, is just substituting the time of 22 in, and we come up with a value of $2,841. So we graph that forecast and it looks like this. And automatically we can see a problem. The power of linear trend projection is that it's generalizable. The downside of linear trend projection is that it's generalizable. So in this case, where our time series has a bend to it, it's pretty straight from the year 2000 all the way up to the year 2014, but then it bends downward. But the best fit line tries to even out above and below the line, and therefore at the end, when it dips down, we have this really strong over forecast. It is quite unlikely that from the year 2020 to the year 21, that the GDP per capita will shoot back up to above 2,500, much less 2,800. But again, this is the nature of linear trend projection. So always know your errors. Forecast errors create a new derivative time series that can be a treasure trove of information for you, the analyst. By looking at just the forecast errors, you should be able to reverse engineer how the underlying time series looks. In fact, many forecasting techniques do this very thing under the hood. Patterns in the errors can reveal trend, seasonality, inflection points, etc. Examining forecast errors can help in the selection and interpretation of other forecasting techniques. So this is a perfect example. We can see that our linear trend has some issues in terms of forecasting. So this may tell us that we might need a curvilinear model, so a polynomial, and see how that works. So by looking at the errors, it might inform whether or not we should use a different technique. So here are the naive forecast errors. So in previous videos, we went over all these forecasting techniques. The naive is the simplest. It's just the previous period moved forward one period in time. We can see that on the left, our actual values were above the forecast values, and on the right, the actual values were below the forecast values. And that's because the time series is just shifted over one time period, and the naive forecast has a hard time keeping up with itself, shifted forward one period in time. So as I mentioned in prior videos, these next few slides are designed to morph into each other so you can see how the bars change from technique to technique. So next we'll look at the moving average. So here the 3-period simple moving average forecast errors are very large. You can see that the bars on the left went up, the bars on the right also increased even though they're inverted. So the 3-period simple moving average was not any better. It was actually quite a lot worse than the naive forecast. Next we have the 3-period weighted moving average forecast errors. Let's see those. Well, you can see that the bars on the left, the yellow bars, got smaller, which is good. And also on the right, the blue bars got smaller, even though they're inverted. So as compared to the 3-period simple moving average, the 3-period weighted moving average was better. Now let's look at the exponential moving average. Better still. So the exponential moving average we did in the prior video, we used an alpha of 0.8, and we see that the bars on the left got smaller still, and the bars on the right in the blue also got smaller. So overall, the exponential moving average was better than the simple moving average and the weighted moving average. But even though it was better than those, it was not better than the naive forecast. Now let's look at the linear trend forecast errors. This is a very different looking graph for our errors. We can see that on the left, we have negative errors, In the middle, we have positive errors, and then on the right, we have negative errors again. And if you remember our graph, it was very evident that the line cut through the data so that it balanced itself out. On the left-hand side, where the errors are negative, our linear trend projection is above the actual. In the middle part, it's below the actual. And then on the right-hand side again, it's above the actual. So remember what I said earlier? That linear trend projection, by its very nature, wants to balance out the errors as it goes through the data. So what we have here is that on the ends of the data, we have negative forecast errors, and in the middle, we have positive forecast errors. When we compare all the errors for those techniques, they look like this. So this orange bar here is the naive forecast errors. The gray bar is the 3-period simple moving average forecast errors, which are a lot taller. Then we have the 3-period weighted moving average errors in that yellow color, a little bit better. Then we have the exponential moving average, they're in the blue, better still. And now we have the linear trend projection errors there in the green. And you can see that the errors on the ends are very, very large. But in the middle, they are very small. So at time period 5, 6, 7, they are very small errors. Then of course, as it goes, they get larger again. So this is just the nature of linear trend projection. We're looking at the entire time series as a whole, like a snapshot. We are modeling it. Whereas in the other techniques, so the naive, 3-period simple, 3-period weighted, and exponential, we are iterating through the time series one by one, applying weights, doing some averaging, and essentially those techniques have no knowledge of the future values at all. Whereas the linear trend projection model looks at everything, everywhere, all at once. And yes, I did work that into this video. So it is quite a bit different in how it creates its forecasts. So here is our forecast accuracy matrix. We can see that linear trend is there in the bottom row. While not the worst in terms of the mean absolute error column, it's pretty close to the 3-period moving average, which is the worst. And it fits right between that 3-period simple moving average and the 3-period weighted moving average. Now in the root mean square error column, we have a different story. The linear trend projection is worse than all the others. Now think about why that is. Remember, in linear regression, and in this case, this is sort of a variation of linear regression, because we square the errors, we penalize large errors heavily. That's why in root mean square error, the linear trend is the worst, because we have those very large errors that we then square, and therefore the root mean square error is very large. In terms of the mean absolute percentage error, we can see that at 6.2, it's not the worst, but again, it falls between the 3-period simple and 3-period weighted. For the MASE or the maze, we can see that it is between, again, the 3-period simple and the 3-period weighted at a value of 1.79. Remember the interpretation of the maze. We are comparing a forecasting technique essentially to the naive forecast. That's why the naive forecast has a maze of 1. So we can say that any value over 1 means that that technique is worse than the naive forecast. And in this case, the linear trend projection has a value of 1.79, which again falls between the 3-period simple and 3-period weighted. So as far as the SMAPE goes, the symmetric mean absolute percentage error, same story. It falls between the 3-period simple moving average and the 3-period weighting moving average with a value of 6.11%. All right, that wraps up this video on linear trend projection and time series, a very visual approach. So I hope you can see, if you work with linear regression, that this technique should be very familiar to you. It's just putting a best fit line to the time series and then projecting forward one period in time. So I hope you found this video helpful. If you did, please like, comment, share, and subscribe, and I will see you again in the next video. It has been a pleasure. Take care and bye-bye.